Okay, everybody, welcome back to the Glen Sebastian Nature Trail. I'm standing right here next to monitoring well number 2, and I'm getting ready to do what's called a well test, and in particular, I'm going to be demonstrating how to do a slug test. So in lecture, if you've kept up, what we're talking about is Darcy's Law, and Darcy's Law provides a way for us to calculate the groundwater velocity, which is really nice. Now, in a previous lab, you guys talked about how to determine the groundwater direction. If you'll recall, we used the contour maps to indicate that water is flowing from the land over towards this pond over here and giving that base flow that we see leaving that pond. But we can get a lot more quantitative. Darcy's Law allows us to calculate the groundwater velocity, and there's two things that we need to be able to calculate groundwater velocity. One is we need hydraulic conductivity, uppercase K in other words, tells us how readily water will move through this aquifer. It's something you actually calculated in the last lab with the well installation with our D10 data and the Hazen formula, if you remember. And the second thing that we need is we need a gradient. We need that DH over DL. And that's something that I'll actually talk about separately in another video, but it's something that we can calculate using our previously collected water table elevation data. And we could even use our contours if we wanted to. Back to hydraulic conductivity. So hydraulic conductivity tells us how readily water can move through our aquifer. So how quickly that water can make its way through the passages and the pore throats of our sediment in this case. So one way that we can get at hydraulic conductivity is to actually use our well and do what's called a well test, where we modify the level of water in this well and we see how quickly the aquifer responds. So let's say I pulled out a bunch of water from this well. The aquifer should flow water back into that well. It'd be like base flow for this well, if you will. And the faster that this well responds, the faster that water fills back up this well, the higher the hydraulic conductivity. Now, I could do the opposite. I could pour a bunch of water into this well and let it inject itself into the aquifer, and the same thing should be true. The higher the hydraulic conductivity of the aquifer, the faster the water will drain out of this well and recharge the aquifer. So that's really the premise behind an aquifer test. We modify the water level inside of the well, and we see how quickly the aquifer responds. So there's a couple different ways of doing these well tests. Probably the simplest is what's called a slug test. Now, slug has various meanings outside of hydrology. You might think of an animal. If you're a hunter, you might think of something that you put inside of your shotgun. Slug is basically just something that takes up space. That's really what it is. So we can use then what's called a slug to take up space inside of our well. In other words, to displace water. So let me show you a little bit more about what I'm talking about. This is a very small, I guess I'd call this a micro slug, just an object. Only purpose for this slug is to take up space. Now, if I were to, and I'm not going to do it because this one's been cut off, but if I were to drop this into the well and let this fall down below the water level in the well, well, what's going to happen is the volume of this object, which is something we can calculate, we don't necessarily need to, but it be pi r squared times h, it's a cylinder. When this falls underneath the water, it's going to displace an equivalent volume of the size of this slug. So in other words, the water is going to rise up, okay? That's how we modify the water level in this well, and we just keep track of that water level and watch that water drain into the aquifer. It's going to try and re-equilibrate itself with the level of the water table in the aquifer. So the faster it drains, the higher the hydraulic conductivity. So that is an example of what we would call slug in, a slug test where we place the slug in, and we always do that first when it comes to slug testing. Drop this thing in, we see the water level rise, we let it drain back down to its equilibrium value. Then we can actually get two for the price of one. What we can do is we can do what's called a slug out, where we pull the slug out after it's reached equilibrium. And what happens is, well, exactly like you might predict, we've now removed that displacing volume. We've removed the slug that takes up space, and the water level will drop as a result. And we can measure how quickly it takes the aquifer to fill that well back up with the missing displaced volume. So this is a version of a small slug. This is something that I use in my research when I'm working with the piezometers. The piezometers have a narrower diameter, a narrower radius than our monitoring wells here. So I don't need quite as much of a slug. I don't need quite as much volume to get the same response. But when it comes to these monitoring wells, I need something a little bit bigger. So the mini slug here, here's a larger slug. This is what we're going to use today. Okay, so you can see it's probably about 3 or 4 times the length. And by the way, both of these slugs are handmade. You could make your own. I actually had a student several years ago make these as part of a research project we're working on. And they work just fine. All it is just PVC pipe, glued caps on both ends, a rope so we don't lose it down the well permanently, cross your fingers. And this thing is full of sand, so heavy enough to sink quickly. We want an immediate response. So this will give us slug in. This will also give us slug out. So we got everything that we need. Now, I want to mention there's another technique that we can use. We're not going to do it today. But you can use, and I've talked about this before when we were installing the well, I've talked about what's called a baler. And a baler bales water, okay? It's basically like a bucket, but it's got a ball inside of here and an opening in the bottom. So when you drop this into the water, water will flow through the bottom. This ball will get pushed out of the way by the water that's trying to enter the baler. And it will fill itself up, and then when you go to pull this out of the well, it will be full of water. The ball gets trapped down in the bottom, and it's basically like a one-way valve. You can use this to bail or pull water out of the well. So that's a good way to get a slug out. Getting a slug in is a little bit more difficult. We could, though, it could be as simple, and again, I'm not going to do it today, but it could be as simple as just pouring water into this well. I've done that before. We take a 5-gallon bucket and quickly pour that water in there and keep track of how quickly that water drains into the aquifer. So that's the slug end. Now, the other thing that we need to keep track of is the water level. So this can be done by hand. If your well is in an aquifer that has a low hydraulic conductivity, so if we were working in some clay or something like that, then I could manually keep track of water level elevation using a depth to water level indicator, something I think we're all pretty comfortable with at this point. And I could watch that water level change or recover from the changes the slug induces. But in this situation, we already know we're working with that really clean sand that we took a sample of. And I've done slug tests out here before. The recovery of this aquifer is going to be very quick. So quick that it's going to be hard for me to keep track of this manually, especially since I'm by myself. I have to not only record, I have to not only measure the changes in the water level in this well, but I would also have to write them down, and that's just a little bit too much for me. So what we're going to use is an entirely automated system, and go ahead and pull it out of the well. We're going to use a piece of equipment that I've talked about before when I was talking about weirs and keeping track of discharge in streams, and I said there's a device called a pressure transducer. It's a pill-shaped device, a little bit bigger than a pill, and this is a piece of equipment that it constantly, it's programmable, but it constantly records pressure. So you can set this up to record pressure on basically whatever time interval you want. I've got it set up right now to record pressure every single second it does it. So that's like having somebody measure water table elevation or depth to water every single second. That's pretty nice, and records it, writes it down for us. But you could go all the way up to, an interval of days, hours. I use 10-15 minutes or so when I'm keeping track of long-term groundwater records for characterizing recharge and base flow in aquifers. If I'm doing a hydrobalance of an aquifer, in other words. So this simple device right here is going to make the measurements of water table elevation, or really water depth, for us. So it will keep track of the changes for us, and this is really now a one-man job. All I have to do is drop this thing down to the bottom, have it tied off somewhere. Give it plenty of slack. You don't want this thing bobbing around or anything like that. You don't want the too much line to be in there because it might interfere with the line from the slug. So that's settled in there. I'm going to go ahead and take a depth to water measurement, and this will be our equilibrium point. The pressure transducer is going to displace a little bit of water, but we should be able to recover fairly quickly given the hydraulic conductivity of this aquifer. Turn the sensitivity up just a little bit here. Okay, so we are at 8.27 feet, 8.27. We check it again. $8.27 feet again. Okay, 8.27 is our depth to water. I wanted to check it multiple times just to make sure that this pressure transducer, when I put it in there, that it's not acting like a mini slug. And that can actually be the case, and it is the case. It does displace water, but if you're working in a clay aquifer, just putting the transducer down there might be the only slug that you need, and the stabilization can take long enough that you can get away with just using that. Now, this is a rapidly recovering well because the hydraulic conductivity is very high. So our well is all set up. The next thing I want to do is take our slug here, take the big one, and I know I've told you guys the kind of rules about working around wells. Wells, it's almost like they have their own gravitational field. They like to just consume things of value or personal interest. So I'm going to tie this slug off. I'm going to use a sophisticated, elaborate setup here. I'm going to tie this thing to a stick. That way, if this slug starts to go, it's going to have to take a stick with it. And I don't think this stick is going to be able to fit through the opening of the well. Okay, so I've got myself a customized stick here. Put this off to the side. Okay, so you guys see my level of supports. I'm ready to go. Make sure that everything is streamlined. I want this slug to enter the well in one fluid motion. I don't want to slowly put it in there. I want to see an initial spike in my water level. That's important for my analysis coming later. So in order to facilitate that, what I'm going to do is I'm going to make sure that everything is out of the way. I'm going to get this pre-charged. And when you do a slug test, it's important that everybody around you is aware of your plans, so that way everything can be moved out and recording can start immediately. So I am going to yell, "Slug out!" Drops down there. I heard a splash. That's a good sign. It rapidly entered the well. Everything's slack, okay? So that slug is underneath the water. It's a good splash. That's an immediate entry. That should be an immediate displacement of water. And we should see, I don't want to give it away, but a characteristic, a diagnostic recovery of that well. It's got a curve, a mathematical function that we've seen over and over and over again in natural sciences and certainly in hydrology. So I'll let you guys guess what sort of shape that is. Now, the slug is in there. I'm going to go ahead and take a measurement of depth to water here. I'll move the lines for the slug out of the way so I can still get to my north points. And we'll just see how we're doing on the recovery side of things. Okay. So I'm at 8.20 feet. I'm now at 8.21 feet. There's 8.22, 8.23. It looks like I'm pretty close. So it looks like recovery is going to go really quickly. So what I'm going to do is I'm going to pause the recording for probably about 5 minutes, and we should be geared up to be able to do slug outs. So I'll just make sure we're back at equilibrium, and then I'll yank this thing out and I'll yell slug out really loudly and hopefully scare some of these people off. All right, so I'm back. I thought it would actually take about 5 minutes, but as soon as I paused the camera, I walked back over here, I checked depth to water, and I've got it all set up now. And you're definitely not gonna be able to see this, but we are back at 8.27 feet. So we recovered this well that quickly. Now, I will tell you again from firsthand experience, that is a quick well recovery. I've done slug tests on sandy aquifers, I've done slug tests on clay aquifers, I've done slug tests on fractured crystalline rock aquifers, and this is about one of the fastest recovering wells that I've tested. So that should give you some indication as to the hydraulic connectivity and also the geologic materials in this aquifer. I've done slug tests that have taken greater than 24 hours to reach equilibrium. And in some cases, after 24 hours, we still hadn't reached equilibrium, but we had enough data to be able to fill in our curve for our analysis. So this one is ready. It's back at equilibrium. It's ready for us to do slug out. So slug in, initial displacement, we've recovered. Now it is time for us to do slug out. So I'm gonna get a firm grasp on this cord right here. And I'm also going to take a peek down here, make sure it's possible, and it might happen to us, I can't make any guarantees, but it's possible to get the line for the slug and the line for the pressure transducer kind of twisted. You want to try and avoid that. If I pull this slug out, I don't want to pull my pressure transducer out, because if it's measuring water depth and it rises, it's going to look like the water is dropping. Okay, but I feel quite confident. If I mess this up, good news is it recovers pretty quickly. I can redo the test in a matter of minutes, but I'm ready to do slug out. So I'll yell slug out, and I'll pull this quickly. There we go. See, it's soaking wet. The slug was all the way under the water. So we pulled this thing out. That's going to cause the water level to drop, and it should be recovering right now. So hopefully you saw my technique, just pull as quick as possible. You can also get the windmill technique is pretty good. I haven't quite mastered that with this double line, but if I was using the baler, that's the approach that I would go for. So slug has been removed. I'm just going to set this aside. Well, looks like it's recovering. Doesn't look like I pulled my transducer, but we'll see when we look through the record from the transducer. And I'm going to drop this water level indicator down here and see how we're doing on recovery. I know it hasn't been very long, but the slug in showed us that we get great response here. So we're at about 8.4 depth to water. That makes sense. The water level has dropped when we do slug out. So the water's going to climb up towards this tape. So 8.4, I'm already down to 8.35 in just the amount of time it took me to explain 8.4. I'm at 8.33. .32 or thereabouts. It looks like I'm at 8.31. So, as exciting as this is for everybody, I'm going to set this aside, and just to be safe, I'm going to let this run for I'll let this run for 2-3 minutes like I did with the first one. I'll come back and check it. If it's 8.27, back at equilibrium, and that's it for the slug test. Now I could do this multiple times, do multiple slug ins, multiple slug outs, but I'm just going to have you guys work with a single slug in and a single slug out to calculate the hydraulic connectivity of this aquifer. Now the second part that I mentioned in getting velocity is we need DH over DL. We need a slope of the water table. And as it turns out, we can work with the water table elevation data that I collected for you for the lab that we did 2 weeks ago when you contoured the water table. And I will show you a method that we can use to get the gradient from just 3 wells. We call it a 3-point problem. Some of you that have had structural geology are familiar with the 3-point problem, and you've probably done several of them before. If you haven't, then it's just a simple way for us to fit a plane a flat surface, in other words, to 3 measurements of water table elevation. So I'll go through with you guys how that is done. That will give us DHGL, or negative DHGL. The slug test will give us hydraulic conductivity, and you guys know by now that the Darcy velocity is equal to negative K times DHGL. So we've got everything we need. If we want to get the seepage velocity or the pore water velocity, we need to use a porosity, and we'll just assume porosity of 0.3. That seems to match what we found based on the type of sediment that's here, which is that kind of fine to medium grained sand. So not a lot of fine materials in here to choke up our porosity. So I guess I ended up talking about it long enough. Let's see if we're back to equilibrium. We are actually back at 8.28 right there. So I will say that is close enough for us. By the time I get this all spooled up and stop recording, I'm pretty sure we're going to be back at 8.27. So I'm going to go ahead and conclude our slug test, and I will see you guys on the blackboard to explain how we're going to take this data and turn this into hydraulic conductivity. You guys might want to start thinking about what equation would best describe the recovery of this well.